In this segment, we're going to look at attacks on the one-time pad and some things you need to be careful with when you use the stream cipher. But before we do that, let's do a quick review of where we were. So recall that the one-time pad encrypts messages by XORing the message and a secret key, where the secret key is as long as the message. Similarly, decryption is done by similarly XORing the ciphertext and the same secret key. When the key is uniform and random, we prove that the one-time pad has this information theoretic security that Shannon called perfect secrecy. The problem was, of course, the keys are as long as the message, so the one-time pad is very difficult to use. We then talked about a way to make the one-time pad practical by using a pseudo-random generator that expands a short seed into a much larger message. And the way a stream cipher worked, essentially using a pseudo-random generator, was in the same way as the one-time pad, basically, but rather than using a truly random pad, we used the pseudo-random pad that's expanded to be as long as the message from the short key that's given as input to the generator. We said now that security no longer relies on perfect secrecy because stream ciphers cannot be perfectly secure. Instead, security relies on properties of the pseudorandom generator. And we said that the pseudorandom generator essentially needs to be unpredictable. But in fact, it turns out that definition is a little bit hard to work with. And we're going to see a better definition of security for PRGs in about 2 segments. But in this segment, we're going to talk about attacks on the one-time pad. And the first attack I want to talk about is what's called the two-time pad attack. Okay, so remember that the one-time pad is called one-time pad because the pad can only be used to encrypt a single message. I want to show you that if the same pad is used to encrypt more than one message, then security goes out the window and basically an eavesdropper can completely decrypt encrypted messages. So let's look at an example. So here we have 2 messages, M1 and M2, that are encrypted using the same pad. So the resulting ciphertext, C1 and C2, again, basically are encryptions of these messages, M1 and M2, but both are encrypted using the same pad. Now suppose an eavesdropper intercepts C1 and C2, and he basically has both C1 and C2. The natural thing for the eavesdropper to do is actually compute the XOR of C1 and C2, and what does he get when he computes this XOR? So I hope everybody sees that basically once you XOR C1 and C2, the pads cancel out, and essentially what comes out of this is the XOR of the plaintext messages. And it turns out that English basically has enough redundancy such that if I give you the XOR of 2 plaintext messages, you can actually recover those 2 messages completely. More importantly for us, since these messages are encoded using ASCII, in fact, ASCII encoding has enough redundancy such that given the XOR of 2 ASCII encoded messages, you can recover the original messages back. Okay, so essentially given these XORs, you can recover both messages. So the thing to remember here is if you ever use the same pad to encrypt multiple messages, an attacker who intercepts the resulting ciphertexts can basically recover the original plaintexts without too much work. So the stream cipher key or the one-time pad key should never, ever, ever, ever be used more than once. So let's look at some examples where this comes up in practice. It's a very common mistake to use a stream cipher key or a one-time pad key more than once. And let me show you some example where this comes up so you know to avoid these mistakes when you build your own systems. The first example is a historic example at the beginning of the 1940s where the Russians actually used a one-time pad to encrypt various messages. Unfortunately, the pads that they were using were generated by a human by throwing dice. And so, the human would throw these dice and write down the results of these throws, and the collected throws would then form the pads that were used for encryption. Now, because it was kind of laborious for them to generate these pads, it seemed wasteful to use the pad to encrypt just one message, so they ended up using these pads to encrypt multiple messages. And US intelligence was actually able to intercept these two-time pads, these ciphertexts that were encrypted using the same pad applied to different messages. And it turns out over a period of several years, they were able to decrypt something like 3,000 plaintexts just by intercepting these ciphertexts. The project is called Project Venona. It's actually a fascinating story of cryptanalysis just because the two-time pad is insecure. More importantly, I want to talk about more recent examples that come up in networking protocols. So let me give you an example from Windows NT in a protocol called the point-to-point transfer protocol. This is a protocol for a client wishing to communicate securely with a server. The client and the server both share a secret key here, and they both send messages to one another. So here we'll denote the messages from the client by M1. So the client sends a message, the server responds, the client sends a message, the server responds, The client sends a message, the server responds, and so on and so forth. Now, the way PTP works is basically the entire interaction from the client to the server is considered as one stream. In other words, what happens is the messages M1 and M2 and M3 are kind of viewed as one long stream. Here, these two parallel lines means concatenation. So essentially, we're concatenating all the messages from the client to the server into one long stream, and all that stream is encrypted using the stream cipher with key K. So that's perfectly fine. I mean, there's nothing wrong with that. These messages are encrypted, are treated as one long stream, and they're all encrypted using the same key. The problem is the same thing is happening also on the server side. In other words, all the messages from the server are also treated as one long stream. So here, they're all concatenated together and encrypted using, unfortunately, the same pseudo-random seed. In other words, using the same stream cipher key. So basically what's happening here is you see an effect that the two-time pad is taking place where the set of messages from the client is encrypted using the same one-time pad as the set of messages from the server. The lesson here is that you should never use the same key to encrypt traffic in both directions. In fact, what you need to do is to have one key for interaction between the client and the server and one key for interaction between the server and the client. The way I like to write this is really that the shared key K really is a pair of keys. One key is used to encrypt messages from server to client, and one key is used to encrypt messages from client to server. So these are two separate keys that are used, and both sides, of course, know this key. So both sides have this pair of keys. Okay, and they can both encrypt. So one is used to encrypt messages in one direction, and the other is used to encrypt messages in the other direction. So another important example of the two-time pad comes up in Wi-Fi communication, in particular in the 802.11b protocol. So all of you, I'm sure, know that 802.11 contains an encryption layer, and the original encryption layer was called WEP. And WEP, fortunately for us, is actually a very badly designed protocol, so that I can always use it as an example of how not to do things. There are many, many mistakes inside of WEP, and here I want to use it as an example of how the two-time pad came about. So let me explain how WEP works. So in WEP, there's a client and an access point. Here's the client, here's the access point. They both share a secret key K. And then when they want to transmit a message to one another, say these are frames that they transmit to one another. Let's say the client wants to send a frame containing the plaintext M to the access point. What he would do is first of all, he appends some sort of a checksum to this plaintext. The checksum is not important at this point. What is important is that then this concatenation gets encrypted using a stream cipher, where the stream cipher key is this concatenation of a value IV and a long-term key K. So this IV is a 24-bit string. Okay, this IV is a 24-bit string, and you can imagine that it starts from 0, and perhaps it's a counter that counts increments by 1 for every packet. The reason they did this is the designers of WEP realized that in a stream cipher, the key is only supposed to be used to encrypt one message. And so they said, well, let's go ahead and change the key after every frame. And the way they changed the key essentially was by prepending this IV to it. And you notice this IV changes on every packet, so it increments by 1 on every packet. And the IV then is sent in the clear along with the ciphertext. So the recipient knows the key K, he knows what the IV is, he can rederive the PRG of IV concatenated K, and then decrypt the ciphertext to recover the original message M. Now the problem with this, of course, is the IV is only 24 bits long, which means that there are only 2 to the 24 possible IVs, which means that after 16 million frames are transmitted, essentially the IV has to cycle. And once it cycles, after 60 million frames, essentially we get a two-time pad. The same IV would be used to encrypt 2 different messages. The key K never changes. It's a long-term key. And as a result, the same key, namely IV concatenated K, would be used to encrypt 2 different frames, and the attacker can then figure out plaintext of both frames. So that's one problem. And the worst problem is, in fact, that on many 802.11 cards, if you power cycle the card, the IV will reset back to 0. And as a result, every time you power cycle the card, essentially you'll be encrypting the next payload using 0 concatenated K. So after every power cycle, you'll be using the 0 concatenated K key to encrypt many, many, many times the same packet. So you see how in WEP, the same pad could be used to encrypt many different messages, as soon as the IV is repeated. There's nothing to prevent the IV from repeating after a power cycle or from repeating after every 16 million frames, which isn't that many frames in a busy network. So while we're talking about WEP, I want to mention one more mistake that was done in WEP. This is a pretty significant mistake, and let's see how we might design it better. So you notice that the designers of WEP basically wanted to use a different key for every packet. Okay, so every frame is encrypted using a different key, this concatenation of IV and K. Unfortunately, they didn't randomize the keys, and the keys are actually, if you look at the key for frame number 1, well, it'll be this concatenation of 1 and K. This field is 24 bits. And then the key for frame number 2 is the concatenation of 2 and K. The key for frame number 3 is the concatenation of 3 and K. So the keys are very closely related to one another. And I should probably mention also that these keys themselves can be 104 bits, so that the resulting PRG key is actually 104 plus 24 bits, which is 128 bits. Unfortunately, these keys are very much related to one another. These are not random keys. You notice they all have the same suffix of 104 bits. And it turns out the pseudorandom generator used in WEP is not designed to be secure when you use related keys that are so closely related. In other words, the majority of these keys are basically the same. And in fact, for the PRG that's used in WEP, that PRG is called RC4. We'll talk about that more in the next segment. It turns out there's an attack that was discovered by Fleurer, Mantin, and Shamir back in 2001 that shows that after about 10 to the 6, after about 1 million frames, you can recover the secret key. You can recover K. So this is kind of a disastrous attack that says essentially all you have to do is listen to about 1 million frames. These frames basically, as we said, they're all generated from a very common seed, namely 104 bits of these seeds are all the same. The fact that you've used such closely related keys is enough to actually recover the original key. And it turns out even after the 2001 attack, better attacks have come out that show that these related keys are very much disastrous, and in fact these days something like 40,000 frames are sufficient, and so that within a matter of minutes you can actually recover the secret key in any WEP network. So WEP provides no security at all for 2 reasons. First of all, it can result in a 2-time pad, but more significantly, because these keys are so closely related, it's actually possible to recover the key by watching just a few ciphertexts. And by the way, we'll see that when we do a security analysis of these types of constructions, in a few segments we'll start talking about how to analyze these types of constructions. We'll see that when we have related keys like this, in fact, our security analysis will fail. We won't be able to get the proof to go through. So one could ask, what should the designers of WEP should have done instead? Well, one approach is to basically treat the frames, M1, M2, M3. Each one is a separate frame transmitted from the client to the server. They could have treated them as one long stream and then XOR them essentially using the pseudorandom generator as one long stream. So the first segment of the pad would have been used to encrypt M1. The second segment of the pad would have been used to encrypt M2. The third segment of the pad would have been used to encrypt M3, and so on and so forth. So they basically would never have had to change the key because the entire interaction is viewed as one long stream. But they chose to have a different key for every frame. So if you want to do that, a better way to do that is rather than slightly modifying this IV that just slightly modifies the prefix of the key, of the PRG key, a better way to do that is to use a PRG again. So essentially what you could do is you would take your long-term key and then feed that directly through a PRG. So now we get a long stream of bits that look essentially random. And then the initial segment could be used, the first segment could be used as the key for frame number 1. And then the second segment would be used as the key for, key from frame number 2, and so on and so forth. The third segment would be used to encrypt frame number 3, and so on and so forth. Okay? So the nice thing about this is now essentially by doing this, each frame has a pseudo-random key. These keys now have no relation to one another. They look like random keys. And as a result, if the PRG is secure for random seeds, it would also be secure on this input because these keys essentially look as though they're independent of one another. We'll see how to do this analysis formally once we talk about these types of constructions. Since this 2-time pad attack comes up so often in practice, it's such a common mistake, I want to give one more example where it comes up so you know how to avoid it. And the last example I want to give is in the context of disk encryption. So imagine we have a certain file, and maybe the file begins with, the words to Bob, and then the contents of the file follows. When this is stored on disk, of course, the file is going to get, so here we have our disk here, the file is going to get broken into blocks, and each block will be, when we actually store this on disk, things will be encrypted, and, so maybe to Bob will go into the first block, and then the rest of the content will go into the remaining blocks. But of course, this is all encrypted, so I'll kind of use these lines here to denote the fact that this is encrypted, and an attacker looking at the disk has no idea what the contents of the message is. But now suppose that at a later time, user goes ahead and modifies, basically, fires up the editor and modifies the file. So now instead of saying to Bob, it says to Eve, and nothing else changes in the file. That's the only change that was made. When the user then saves this modified file to disk, basically he's going to re-encrypt it again. And so the same thing is going to happen. The file is going to get broken into blocks. Now the file is going to say to Eve, and everything, of course, is going to be encrypted. So again, I'll put these lines here. Now, an attacker looking at the disk, taking a snapshot of the disk before the edit, and then looking again at the disk after the edit, what he will see is that the only thing that changed is this little segment here that's now different. Everything else looks exactly the same. So the attacker, even though he doesn't know what actually happened to the file, what's in the file, or what changed, he knows exactly the location where the edit took place. And so the fact that the one-time pad or a stream cipher encrypts one bit at a time means that if one change takes place, then it's very easy to tell where that change occurred. And that leaks information that the attacker shouldn't actually learn. Ideally, you'd like to say that even if the file changed just a little bit, the entire contents of the file should change, or maybe at least the entire contents of the blocks should change. Here you can see that the attacker even knows within the block where the change was actually made. Okay, so in fact, because of this, it's usually a bad idea to use stream ciphers for disk encryption, and essentially this is another example of a two-time pad attack because the same pad is used to encrypt two different messages. They happen to be very similar, but nevertheless, these are two different messages, and the attacker can learn what the change was, and in fact, he might be able to even learn what the actual changed words were as a result of this. Okay, so the lesson here is generally we need to do something different for disk encryption. We'll talk about what to do for disk encryption in a later segment, but essentially the one-time pad is generally not a good idea for encrypting blocks on disk. So just again, to summarize the two-time pad attack, we saw that you're supposed, I hope I've convinced you that you're never, ever, ever supposed to use a stream cipher key more than once. Even though there are natural settings where that might happen, you have to take care and make sure that you're not using the same key more than once. So for network traffic, typically what you're supposed to do is every session would have its own key. Within the session, the message from the client to the server would look as one complete stream. It would be encrypted using one key. The messages from the server to the client would be treated as one stream and encrypted using a different key. And then for disk encryption, typically you would not use a stream cipher because as changes are made to the file, you would be leaking information about the contents of the file. Okay, so that concludes our brief discussion of the two-time pad. Next attack I want to mention is the fact that the one-time pad and stream ciphers in general provide no integrity at all. All they do is they try to provide confidentiality when the key is only used once. They provide no integrity at all. But even worse than that, it's actually very easy to modify ciphertexts and have known effects on the corresponding plaintexts. So let me explain what I mean by that. This property, by the way, is called malleability, and we'll see what I mean by that in just a second. So imagine we have some message M that gets encrypted. So here, it gets encrypted using a stream cipher. And the ciphertext, of course, is then going to be M XOR K. Now, an attacker intercepts the ciphertext. Well, that doesn't tell him what the plaintext is. But what he can do is now, beyond eavesdropping, he can actually become an active attacker and modify the ciphertext. So when I say modify the ciphertext, let's suppose that he XORs the ciphertext with a certain value P. Let's call this the perturbation P. Well, the resulting ciphertext then becomes M XOR K XOR P. So now let me ask you, when we decrypt the ciphertext, what is it going to decrypt to? Well, I hope everybody sees that manipulating XORs, basically the decryption becomes M XOR P. So you notice that by XORing with this pad P, the attacker was able to have a very specific effect on the resulting plaintext. Okay, so to summarize this, basically you can modify the ciphertext. These modifications are undetected, but even worse, they're undetected. They have a very specific impact on the resulting plaintext. Namely, whatever you XOR the ciphertext with is going to have that exact effect on the plaintext. So to see where this can be dangerous, let's look at a particular example. Suppose the user sends an email that starts from the words "from Bob." And the attacker basically gets to intercept the corresponding ciphertext. Well, he doesn't know what the ciphertext is, but let's just, for the sake of it, let's pretend that he actually knows that this message is actually from Bob. What he wants to do is he wants to modify the ciphertext so that the plaintext would now look like it came from somebody else. Say he wants to make it look like this message actually came from Alice. All he has is the ciphertext. Well, what he can do is he can XOR it with a certain set of 3 characters. We'll see what those 3 characters are in just a second, such that the resulting ciphertext is actually an encryption of the message from Eve. And so that now when the user decrypts that, all of a sudden he'll see, hey, this message is from Eve. It's not. He'll think this message is from Eve, not from Bob, and that might cause, the wrong thing to take place. So here, the attacker, even though he himself could not have created a ciphertext that says from Eve, by modifying an existing ciphertext, all of a sudden he was able to make the ciphertext that he could not have done without intercepting at least one ciphertext. So again, by intercepting one ciphertext, he was able to change it so now it looks like it's from Eve rather than from Bob. So just to be specific, let's look at what these 3 characters need to be. So let's look at the word Bob, and I'm going to write it in ASCII. So Bob in ASCII corresponds to 42 hex, 6F hex, and 62 hex. So little b is encoded as 62, little o is encoded as 6F. The word Eve is encoded as 45 hex, 76 hex, and 65 hex. Now when I XOR these 2 words, I'm literally going to XOR them as bit strings. So Bob XOR Eve. It's not difficult to see that what I get is the 3 characters 07, 19, and 07. So really what these 3 characters here are going to be are simply 07, 19, and 07. And by XORing these 3 characters at the right positions into the ciphertext, the attacker was able to change the ciphertext to look like it came from Eve rather than from Bob. So this is an example where having a predictable impact on the ciphertext can actually cause quite a bit of problems. And this is this property called malleability. And we say that the runtime pad is malleable because it's very easy to compute on ciphertexts and make prescribed changes to the corresponding plaintext. So to prevent all this, I'm going to do that actually in 2 or 3 lectures, and we're going to basically show how to add integrity to encryption mechanisms in general. But right now I want you to remember that the one-time pad by itself has no integrity and is completely insecure against attackers that actually modify the ciphertexts.